Hello friends, welcome to Power Electronics. Today we will discuss the phase control rectifiers. As we know, a rectifier is a device which convert AC into DC. But this is not an controllable DC. In many industrial applications such as steel rolling mills, paper mills, printing presses, or traction systems, or high voltage DC transmission, or portable hand tool drives, or magnet power supplies, we need one thing, that is controllable DC. In previous earlier DC power was obtained from motor generator sets with the help of mercury arc rectifiers. With the upcoming of the thyristors, it has completely changed the art of AC to DC conversion. Phase controlled AC to DC converters employ thyristors, which are mostly used everywhere. As per the modernization, the mercury arc rectifiers and thyratron tubes are replaced by the word called thyristor. So thyristor, we required a controllable DC. Now in phase controlled rectifiers, how do we turn off the thyristor? It is turned on by applying a voltage reverse bias, which will provide anode current has fallen to a level below the holding current. I have already discussed the holding current. It is the minimum value of the anode current below which thyristor do not conduct. For example, the holding current here is 100 milliampere. So we require 90 milliampere for the thyristor to stop conducting, and with the condition is the gate supply is removed. So how to turn it off the thyristor? It is by the applying a negative voltage and making this current, anode current, fall below the holding current. So a thyristor by supply voltage itself is called as natural or line commutation. In industrial application, rectifier circuit make use of more than one SCR. In such circuits where an incoming SCR is turned on by triggering, it immediately reverse biases the outgoing SCR. So we have taken some of the conditions while we study this. First of all, first condition is that there is no voltage drop across them. No voltage drop across the thyristor. Second one is no reverse current exist. No reverse current exist. Third point here is that T on and T off should be 0 and holding current is 0. But practically this is not possible. There is always a drop across any other device. If we take, there must be some kind of drop if current flows through the device. And reverse current is also available because of the inductor and capacitor, because they have property to change its polarity. Also the holding current is not absolute 0, it is just below, so that the thyristor stop conducting. So we will discuss its principle of the phase controlled rectifiers. As you can see in the diagram, there is one thyristor T with voltage Vm sin omega t, as this is an supply with the resistor R and the voltage V naught. As we have already studied in the previous classes, when the anode is positive with respect to cathode, the thyristor starts conducting unless until we do not supply the gate supply. Whenever we give the gate supply, it starts conducting and the anode current start flowing through it. Here V naught is the maximum voltage Vm sin alpha. Here, as you can see in the diagram, that this is the Vm sin omega t, this is the sine wave, and we have to give the pulse firing. We have to pulse fire at a particular angle, that is called an alpha. As you can see here, by the alpha we fire it. When we fire it, it starts conducting. It conducts from alpha to pi, as you can see, alpha to pi. So what do you mean by the conducting time or firing angle? May be defined as the angle measured from the instant that gives the largest average output voltage to a instant it is triggered. That means for a larger average value it starts conducting, or we can also say by it other definition that firing angle is measured from the angle that gives the largest output voltage or the highest load voltage. Or we can also say that the firing angle may be defined as the angle measured from the instant the SCR gets forward biased due to the instant of triggering. So where we trigger it, it triggered at the angle alpha. We have given the firing pulse. So this is the output voltage you can see. Also the load current and the what is the voltage across the thyristor. As we know that here we have to calculate the output voltage V naught. As you can see V naught, we have to calculate the average power. So average power, how do we calculate? It is the area by the time period. Here the time period is from 0 to 2 pi. So we will take 1 to 2 pi. How many times from where the thyristor is conducting? It is conducting from alpha to pi. So its range is from alpha to pi. As we know, the supply voltage is Vm sin omega t d omega t. When we integrate, we get this Vm upon 2 pi 1 plus cos alpha. Consider the value of alpha to be 0. Cos 0 is 1. So whatever the value is Vm by pi. So its maximum value is Vm by pi. So that's why we calculate the output voltage. It is the Vm by 2 1 plus cos alpha. As we increase the value of alpha, we can get different outputs. So we know how to calculate the area. As we know, area, this area upon the complete time period t. That's why we can calculate it. And also the load current. How do we calculate I naught? We calculate is V naught divided by R. So we have divided Vm, that is a maximum, upon 2 pi R 1 plus cos alpha. Up to this we have calculated the average load current. Again we, if look at the diagram in the figure, that we can see that when we have triggered at this firing angle alpha, what do we have observed? That it starts conducting from alpha to pi in the output. Also same, the load current also conducting from alpha to pi. At the from pi to 2 pi it stops conducting. Why? If you can see in the circuit diagram that the thyristor starts conducting, here it passes through the thyristor, then it goes to the resistor and then the back path. This thyristor act as a short circuit. But when the supply changes, this thyristor will not work, it act as an open circuit. So at that particular point of time from pi to 2 pi it stops conducting. So if you can see what the voltage we get across the thyristor is, that thyristor is short. You can see this thyristor is short because it is conducting. Also the firing angle, we can see this is the firing angle. Also at the negative supply, there is a voltage minus Vm across the thyristor. So you can see that from pi to 2 pi, where the thyristor is not conducting, the voltage across it is minus Vm. So we just, if we simplify this, remove the output voltage from the supply. If I remove this part here, if I remove this part here, then I can see the diagram similar to it. You can see the diagram, it look like same as the output, it is same. Then if I remove this part, I can see this, the voltage is same as the voltage across the thyristor. So we have calculated the average load. Then how do we calculate the RMS value? RMS value means the root mean square. First of all we square, then we take mean, then we take root. So as you can see in the diagram here, that this is an area, so we will square it. The area is Vm sin omega t. We will make square of it, then divided by the time period. What is the time period? Time period is 2 pi, 1 upon 2 pi. It ranges from alpha to pi. And also we have to take root of this. So here in the equation you can see 1 by 2 pi. From alpha to pi it's conducting Vm square sine square omega t d omega t, and we have taken its root. So this is called as root mean square value. When we integrate it, we get a value of RMS value equal to Vm 2 under root pi, pi minus alpha plus 1 by 2 sine 2 alpha 1 by 2. So if you have to calculate the RMS current, then just divide it by the resistor R. Power delivered to the resistor. What is power? We know that it is voltage into current, that is RMS current, RMS voltage into RMS current. So as we know what is the value of the current, that is we put the value from here, VOR, that is RMS square upon resistance, then we get this value. Input volt ampere, that is RMS source voltage into the true RMS line current, then we can calculate the input volt ampere. The input power factor, that is how we calculate it, RMS value upon this the source voltage into RMS. So what we get, this both RMS currents will cancel out, we get V RMS upon V supply voltage. Also the input power factor 1 by 2 pi, pi minus alpha 1 by 2 sine 2 alpha 1 by 2. So that's why we can calculate this value. So thank you very much. I will discuss its numerical in next classes.